want to talk to you guys about choosing a reference frame. You guys have been doing this for a while, although we basically do it on instinct. We're actually making some choices when we do this. So I have a block sitting here, and if something pushes it, then usually we say that this way is positive, and we call that the x direction, and then we call, we've got the normal force pushing up here, the force due to gravity pulling down here, and we call this way the y direction. We usually call it positive, and that makes sense. And when we switch to the vertical direction, we do exactly the same thing. We don't have to worry about x, but we usually say, all right, y is this direction and x is this direction. Why do we pick things like that? Well, we pick things like that because the motion is in those directions, and when we do that, it makes our life easier. But we could just as easily have picked our y direction to be this way and our x direction to be this way. And then we'd have to deal with the components of those things in those directions. We don't generally do that unless there's a reason that it would help us. So we can actually choose a reference frame however we want. And there's a couple rules that we have to keep in mind when we do this. The first thing, x needs to be perpendicular to y. That way we can use the Pythagorean theorem to add vectors that are in x and in y, and then we can use trig for right triangles. So we keep our x and y perpendicular. And the second thing we want to do is pick the reference frame to make your life easier. And what I mean by that, and when I say your life, I mean to make the math easier. Pick the frame to make the math easier. Let me show you what I mean. If we go to a block that's on an incline, all of a sudden I have to deal with things that are moving in more than one dimension. Because if this is my frame of reference, I have y here, x here, and this is positive, then I've got to deal with a whole bunch of forces. And let's actually just let's make this a cart so that I can, we know it's going to move, right? So, we're going to draw in all the forces that are acting and see if we can deal with that. Here's the force due to gravity. Let's say that there is a little bit of friction. Friction always acts parallel to the surface. So Fk. Here is the normal force, Fn. And remember, it's perpendicular to the surface, so it doesn't push against gravity. It pushes perpendicular to the surface. Now, I want to know the acceleration of this thing. Well, it is going to accelerate this way. So if this is my frame of reference, what I have to do is I have to say, well, net force in x equals mass times acceleration in x, and net force in y equals mass times acceleration in y. So let's find everything that acts in x. Well, Fk doesn't act in x, but it has components that act in x because we have Fk going up the incline. So I'm going to draw that just a little bit bigger. X is in this direction and in this direction. So I have Fk, x, and I have Fk, y. Same thing with the normal force. The normal force doesn't act in x or y, but it has components that act in both. So I can draw this one here, and I can draw this one here. I have Fn, y, and Fn, x. So then when I come to find my net force in x, what I have is Fk, x, and it's negative, it's pulling one way, plus Fn, x equals max. And then I have to find the angle here, if I know the angle here, and find all those forces. And in y, I'm going to end up doing the same thing. I'm going to have the net force in y equals mass times acceleration y. Well, in y, I have Fky, it's this one pulling up, minus Fg plus that one, plus Fny equals may. And now I have to do a whole bunch of trig in order to get these things to cancel. And when I'm all said and done, I'm going to have an x component of acceleration and a y component of acceleration, because this thing's accelerating this way, which really means it's accelerating in x and in y. Well, we can make this problem a whole heck of a lot simpler if we actually choose a direction in which the acceleration is. So what I mean by that is last time I drew x and y like this, and I had my positive x value here and my positive y value here. If instead of doing that, if I draw my reference to actually be parallel and perpendicular to the surface, it changes what has components and what doesn't. So let me draw my card again, and you can see I'm going to draw exactly the same forces I have the normal force, I have the force due to gravity, and I have friction. But now, I actually have these things in a direction instead of in multiple directions. So when I go to find the net force in X, there's only one force that actually needs to have components. It's Fg. Fg has an X component, and Fg has a Y component. So when I find the net force in X, it's Fgx minus Fk equals ma in X. And when I find the net force in Y, what I have is Fn, and all of it, because it's parallel in my Y direction, minus Fgy equals may. And now there's one more benefit to this. This thing's going to accelerate down the track. It's not going to jump up off of that. It's not going to fall through it. So that means the acceleration in y is 0. So now I actually know my normal force is just equal and opposite to my y component of gravity. So I actually can solve this a lot faster now because I rotated my frame of reference to be in the direction or parallel to the direction of the acceleration.